Welcome back. So here is my title, Quantum Computing for Sustainable and Energy Materials. So I'm from Arizona State University, so I'm running quantum mechanical engineering lab in my university. So here is my email and my web link. So first of all, some background. So my group has a mission to help solve sustainable issues. So here are some images related to sustainable issues. So as you can see, extreme weather, flood, drought, and wildfire. So we know that those important sustainable issues are related to climate change. So what my group is doing now is try to discover new material to help solve these issues. So for example, we try to discover some new materials that can capture carbon dioxide from the atmosphere. So as you can see from the next picture here, there are so many candidates. There can be some liquid, some solids that can help capture carbon dioxide. And on the right-hand side here, you see two pictures. At the top, and you see future hydrogen economy, right? And you want, because the cost of generating green hydrogen from spring water is going to decrease. And when this happens, and it's actually happening right now, how can you transport or store this green hydrogen? It will become an important issue. And we also know that we can use semiconductor to capture sunlight and then convert to electricity. And all those materials are related to materials. So what my groups are doing now are divided into two themes. The left-hand side, we are developing quantum counterparts of cutting-edge machine learning algorithms. So for example, we try to develop some quantum attention mechanisms so that we can identify some important elements from the periodic table and to form some potential materials to help solve those sustainable issues. On the right-hand side here, you see the picture. So we also applying existing quantum chemistry methods, right? So basically numerically solve Schrodinger's equation, and then you can predict the electronic behavior, and then to predict material behavior before a material is experimentally made. And what are the challenges of this material discovery? So we know there are over 100 elements in the periodic table. We haven't considered their ratio yet. If we consider the combination of those elements and the possible molar ratios of those elements, it will form a very, very large so-called compositional space. So how can we identify the optimal combination of elements and determine their molar ratios from this large compositional space to identify potentially useful materials? And today I'm going to show you one example of material discovery. So this family of materials is called high entropy materials. So you can imagine we usually use conventional material, and in those conventional materials, you usually have one dominant chemical element and the other minor addition of elements, such as iron, right? You have over 90% of iron, and then very small amount of carbon to modify the property. But in high entropy materials, or HEMs, you have many elements, and those elements have similar molar ratio. So for example, copper, gold, and other elements, they have almost the same molar ratios. So why people want to mix so many elements together? So first of all, when we have more elements, usually you will have more properties coming out of these more elements, right? And we also know that for conventional material, usually if you want to get some high strength, usually it's at the cost of ductility, or vice versa. If you want a high ductility, it's usually at the cost of the strength. So it has been shown experimentally that if you have many elements combined together, you can overcome this strength and ductility trade-off. Okay, and here I show you other possible applications of high entropy materials. So we know chips are everywhere, right? So the computers we are using now, the cell phone we are using now, they have chips, and chips are based on semiconductors. And semiconductors, in the figure here, you see in the illustration, you have many components, and one of the key components is, as you can see here, high K insulator. So basically, it's made of some oxide. And we want to increase the K here, means the dielectric constant. We want to increase the dielectric constant. Usually, one oxide usually is not sufficient. So people try to mix different oxides together in order to enhance the dielectric constant. So essentially, they are using this high entropy oxide to achieve this high dielectric constant. And I mentioned earlier that we need to figure out some way to store hydrogen. Right? Currently, people use ion, but there are a lot of issues. So, for example, hydrogen can cause the brittleness of ion. Right? But it has been shown experimentally that if you combine those elements together, you will have a high adsorpability of storing hydrogen, and other combination of metals. You can also overcome this hydrogen embrittlement issue. Okay. And as a material scientist, we are really concerned about microstructure. So what do I mean by microstructure? So microstructure means that you can essentially means the arrangement of atoms and the atomic scale. So here I show you the challenge of designing high entropy material. One example, which is called phase prediction. So you can imagine you have three Lego blocks. Right? You combine three elements together, and typically you will get three microstructures. So the first microstructure here is called a solid solution. So essentially you can imagine this is you dissolve sodium chloride in water, so everything is homogeneous and atoms randomly distributed. So this phase or this microstructure is typically preferred, but we know it's very hard, right? Because some atoms, when you mix together, they prefer to be together. Okay, and another possibility of microstructure you will get is so-called intermetallic compound. But everything is very ordered, represented by the small square and the top left corner here. Right? This is typically people try to avoid because intermetallic compound is usually brittle. Right? So order is brittle. And the third possibility is when you mix those three elements together, you will get a mixture of both those two microstructures. So we are trying to figure out one way to tell you, oh, if you just randomly mix several elements together, how can I tell you in advance which microstructure you will get? Right? And you can solve it using classical machine learning. So to do classical machine learning, you can collect this kind of data. And here is the snapshot of the data. The first column shows the chemical formulas. Right? So for example, the first compound is silver, aluminum, cobalt, chromium, copper, and nickel. And you can also collect and also calculate their corresponding features for classical machine learning. And the last column shows one of the three possibilities. So those data can be either calculated or collected from experiment. So we are essentially doing supervised machine learning calculations. Okay, so classically, it's quite straightforward to do, right? So you have some input, you try to predict three categories. It's very similar to, oh, you have a bunch of images, try to predict the handwritten digit, very classic. So here you input a bunch of struct features and try to predict 103 categories. And you can just set arbitrary number of layers in between and arbitrary number of neurons in each hidden layer. So here is the performance of classical machine learning. So you can see if you do ternary classification, you get 70%, and then binary, you get those accuracy values. Okay. And you can improve the testing accuracy by adding more input features, right? Because based on your chemical or physics intuition, you can add as many input features as you can, as far as you think is related to your category. So here, what we did is you add an extra input feature, then you can improve the testing accuracy. Okay. Although the overall testing accuracy is low, but we can compare against the empirical method. Right? Empirical method here, so many data points, they're supposed to be in this region, but they were wrongly predicted in that particular region. So this is based on empirical method, you get 60% is lower than the prediction accuracy using classical machine learning. And we also try to see which features can play the most important role in affecting the testing accuracy. Right? We use a deductive method by you can remove the input feature one by one and then retrain the model and to see how the testing accuracy is affected. And you can see here one of the features, especially the middle one here, is atomic radii difference in affecting the testing accuracy the most. So we try to do interpretable machine learning. And now I move on to using quantum computers to do the same classification task. Right? We know that we have been through agricultural age, industrial age, and now we are silicon age, and it's arguably in the future age is going to be quantum age. Right? I mentioned earlier that we have so many elements to choose from the periodic table. It's very typical combinatorial problem, and quantum computers are intrinsically promising to solve these combinatorial problems. So we are going to apply quantum machine learning to solve the same task. So this is just a slide to remind you what we are trying to do. But here, we don't input the input features. The only input here is chemical formulas to one of the three possible categories. In other words, we didn't encode anything about the input features here, right? In classical machine learning, you not only have these chemical formula, you also have these input features calculated by constituent elements. But here, we only want to input chemical formula to one of the three possible categories. Right? That might sound crazy, but it has been shown classically that you can map the sequence of amino acid to the shape of proteins, right? So this is a very famous paper, AlphaFold. Right? The only input is the sequence AlphaFold. They ignore the details of the atomic arrangement in each types of amino acid. They can accurately predict the final shape of the proteins. Right? So it's doable classically. If it is doable classically, I don't find any reason that you cannot do it using quantum computers. So that's why we try to map these chemical formulas to one of the three categories. Okay. So first of all, how to represent chemical formulas in a quantum circuit. So here is one of the encoding scheme. Right? You have chemical formulas. Right? So for example, this compound has 5 elements, and 4 of them has the same molar ratio, and 1 of them is half of the other 4 elements. Right? So what we did is you can make a list of available elements in the database. So we have 27 elements here. And you can also make a list of the corresponding molar ratios. Right? You can see here some of the numbers are 1, and one of the numbers is 0.5. They represent the molar ratio. Right? And then we can apply those parameters to a rotation gate in a quantum circuit, right? And then this notation gate is represented by 3 parameters, psi, theta, and omega are there. Right, so, and since we have 27 elements in the database, so we can divide these 27 into 9 sets of 3 numbers. Right, essentially, you have one arrow, you rotate it 9 times, and it represents 1 compound. Here, we only use 1 qubit to represent a compound with 5 elements. Okay, and then we try to compare the accuracy from this quantum machine learning calculation against the accuracy from a typical deep learning neural network. Okay, so on the top panel here, it shows the classical machine learning architecture. The bottom panel here shows the framework for our quantum machine learning. So each input is a 3. It's 3 numbers representing those 3 parameters I showed you earlier. So you do the input 9 times, then you have a compound. And we use a hybrid algorithm, which means that we are going to make a quantum processor talk with the classical processor. And classical processor CPU here provides parameters to quantum processor. And we also need to encode the 3 categories. So that's straightforward to do, right? You can use loss power to represent one of the 3 phases, and x and y axis in the Bloch sphere to represent the other 2 microstructures. And you can also define a loss function, and you can use CPU to optimize these parameters. So here is the slide showing the comparison. So the top 2 panels showing the classical neural network, and the bottom 2 panels shows quantum machine learning implemented in simulator. So you can see here, if you only look at the testing accuracy converged to around 65%, is similar to 65% shown at the top right here. And so here are the results using quantum hardware. So different from simulator here, 65% using quantum hardware. It's expectedly you will get the accuracy that's lower than a quantum simulator, only 50 something. You also notice that the number of epochs here is not very high because there is a lot of time cost when we wait there to connect to IBM quantum computer and then to receive the results. So we only had around 10 epochs in the x-axis. Yeah, so here, I just show you a case study that try to convince you that you can use quantum computer to do material discovery to contribute to our sustainable future. And I show you, I hope I show you very convincing example that you can, because there are so many elements in a periodic table, you can use quantum computer to solve this combinatorial problem. So with that, I will stop here, thanking my students who did the work, and also thanking the funding agency and IBM Quantum to support my research. Thank you.
Is there any question?
So when you encode your solutions in the X, Y, and Z space, go back a little further. Yeah, that one. So when you do a measurement, how do you know which basis to measure in? Because if you measure in the Z basis, I would always conclude it's SS, right?
How do I?
If you measure in the Z basis, you can only measure 0 and 1. So if the resulting vector is in the Y, then you, no matter what, measure a 0 or 1.
Okay. Oh, you can check the amplitudes, right? You can no. Oh, you have a very good point here. You can measure in a different basis, rather than
Yeah,
this.
but how do you know which basis to measure in?
Oh, you can set in advance.
All right.
Yeah, you can set in advance. I can show you the details. Yeah.
Great.